This meeting is being recorded.
So let's take a look at some more aspects of aqueous equilibria that we have not seen yet in this or previous chapters. The last video, we introduced this concept of the solubility product constant, this KSP value. And it's important to note that this is not the same thing as solubility. This is a constant, which we know is constant at, say, 25 degrees Celsius. But solubility, this is expressed as the mass of a solute per 1 liter, so grams per liter or grams per milliliter, not in moles per liter. So solubility, the take-home note here is that our solubility can change with temperature and pH. So these are not the same thing, and we can use things like molar mass or concentrations to kind of convert between these. So if we have our grams per liter, our mass solubility of our compound, if we know the molar mass, we can find the molar solubility. If we have the molar solubility, we can find the molar concentration of ions, and then from there, find our KSP value or our KSP expression. So let's take a look at the sample exercise below here for sample exercise 11. And we'll see an example of some of these conversions between different values, between KSP or molar concentration. So we're given some information here. We're told that at 20 degrees Celsius, we have a saturated aqueous solution of silver carbonate. So let's start drawing our dissociation here. So silver, again, is that +1 ion, carbonate, -2. So we get this solid molecular formula here. We add this to water, we ionize as much as we can. We're going to get 2 silvers for every 1 carbonate. Now, this is our dissociation equation. So our KSP is going to look like this. Concentration of silver ions. Now I'm going to square this. If you recall with other K values, other constants like Kp, Kc, any coefficients become exponents. And then here we're going to have our carbonate concentration. So let's see, what are we given? What else are we given? We're given 32 milligrams per liter is our saturated solutions value. So that's going to be our how much is soluble, right? So to create a saturated solution, all that is soluble will dissolve. So that's how we know that this is our how much is dissolved in our solution. We have 32 milligrams because we're told we have saturated solution, and that's in 1 liter. Again, this is our Ag2CO3. Now, what else are we told here? Well, we know that there is 1 gram per every 1,000 milligrams. So we can convert here to grams. So we're going to just divide by 1,000, and we can keep moving along here. And I will show you in a moment why I did this. So now I have grams per liter, and then if I use my molar mass, so I have blank moles, right, or 1 mole rather, for the molar mass is 275.8 grams. Now these grams will cancel, and I'm going to end up with a unit of mole per liter. So that's what we were asked to do in this step here, solve for KSP. First, we need to solve for the molar concentration. So now we get this value, 1.16 times 10 to the -4 molar. And that's going to be for every 1 mole that we receive ions here. So this will be the concentration for our carbonate. But we're going to need to multiply this by 2 to account for that every 1 mole of silver carbonate, we get 2 moles of silver. So we're going to say 2 times 1.16 times 10 to the -4 molar gives me 2.32 times 10 to the -4 molar. So now I have enough values. This is my silver to plug into my KSP expression. and we can calculate our KSP. So it's going to be silver squared, so 2.32 to the negative 4. We're going to square that value. Then we have times our carbonate, that was 1.16 to the negative 4. Right, so we square this and then we multiply, we find our product. The KSP for silver carbonate turns out to be 6.2 times 10 to the negative 12.